In this segment, we're going to talk about an extension of the self-attention mechanism, which is going to allow us to make it more general and more powerful and generally use it as a strong component of modern neural networks. So one of the drawbacks of attention, as we've seen so far, is that while it can theoretically look at a long context of information and mix a lot of different information together, in practice that doesn't always happen. The distributions that come out of softmaxes tend to be very peaky, partially because it's hard to balance the values of different logits very precisely when they're sort of computed based on different inputs. So in reality, what we kind of want for language modeling in a situation like this is if you're saying, I visited new blank, we really need to know that this is like a place that's new something, and it's a place maybe that I visited or I want to visit, right? So, maybe we think that the attention distribution should be something like this, where it kind of places equal weight and on visited and new. But then usually what we end up with is something like this, where it'll kind of like have much more weight on one than the other. And so we're not going to kind of be able to blend information about these two concepts together. So one solution to this is to just stack layers, right? We can have many different layers of the network and kind of over time gradually be able to integrate this information together if like layer 1 looks at new and layer 2 looks at visited. But it would be great if we could get this capability within a single layer of the model as well. And this is what multi-head self-attention is going to allow us to do. So we mentioned the idea of an attention head before, and basically we're just going to copy paste the whole architecture that we had and do multiple independent copies of attention. So we talked about it as a process that's parameterized by WQ, WK, and WV. Now, what I said is that those were matrices that you could just randomly initialize, and then we're going to learn through backpropagation. But what you can do is you could say, all right, I'm going to randomly initialize two sets of these matrices, right? Just have two different WQs, two different WKs, two different WVs for the same sets of inputs. Now, these are going to compute different queries, keys, and values, and so the attention computations you get are naturally going to be different. So to kind of show it in a little more detail, we take our word embeddings X, and we take all of these different matrices. In this case, we're going to look at 8 copies, borrowing this figure from Alamar. And that is going to then give us 8 different outputs of the attention, Z0 through Z7 here. Remember that these Z's were kind of linear combinations of the values produced by taking the attention matrices from each corresponding Q and K. So at each point here, like these two are going to combine to form something we're going to call A1 that's going to have, some distribution. These two are going to form A0, which might have, a different distribution. So at the end, we get all these Z's, and what we need to do is we need to kind of collapse them all back down. So instead of having a 3-dimensional embedding for each of 2 words, we're going to concatenate them all together. So we actually got a 24-dimensional embedding for each of those 2 words, then multiply it by a matrix and kind of bring it back down to the same size as the input. So now we've got our input and output the same size, but we've been able to incorporate all of this different information from the different distributions that can do things like A1 looks at new, A0 looks at visited. They can look at this these different words in the context, for example. So ultimately, we've kind of achieved our goal here, where we can have one head attend to new, another attend to visited, and this stuff gets all kind of blended together in this model and turned into a new contextualized representation here. And we see now with all these pieces of the transformer in place, it's really enabled us to kind of deliver on this view here of taking this information and using stuff from all throughout the context in a kind of non-uniform way, but still be able to kind of scale efficiently and do so with a small number of parameters. That's the end of this segment.